So first, I'd like to thank the organizers. It's an honor to be able to speak here today. Everything I'm talking about today is joint work with Richard Kent, the University of Wisconsin. And what I'm going to talk about is a project to create an image of Thurston's skinning map computationally. So there's a long history in Teichmueller theory of focusing on low-dimensional examples where it's possible to make meaningful pictures. And because the dimension of the Teichmueller space as a complex manifold is a linear function of the Euler characteristic, if you're going to try to make meaningful pictures, you're really quite limited in which examples you can focus on. To make an actual picture that you can see on a computer screen or on a poster or something of a Teichmueller space, you have to focus on either the punctured torus or the four-punctured sphere. Those have one-dimensional Teichmueller space, and each of those Teichmueller spaces is actually just the upper half plane. If you're trying to understand something like the boundary of Teichmueller space, the space of projective measured laminations, then you can, in some cases, get by with looking at the five-punctured sphere or the twice-punctured torus. In both of those cases, the Teichmueller space is two-dimensional over the complex numbers, and so the boundary is a three-sphere. So, for example, the poster for the Ahlfors-Bers colloquium includes an image showing the space of simple closed curves on the five-punctured sphere realized as a subset of the projective measured lamination space, which is the three-sphere stereographically projected into R3 and then mercilessly projected onto a two-dimensional poster. Okay, so what's the actual focus of my talk today? The goal of this project was to make a picture of Thurston's skinning map, and that's not really the ultimate goal. The ultimate goal is to make a meaningful picture that might suggest things about the skinning map, about Thurston's construction of hyperbolic structures on compact manifolds, where you might learn something from these pictures, but to make a meaningful, accurate picture that allows you to understand Thurston's skinning map in some example. So I'll define the skinning map in a minute, but I'll just remove any dramatic tension from the lecture by telling you which low-dimensional Teichmueller space I'll focus on. It will be that of the four-punctured sphere. The reason for that is that of the two one-dimensional complex manifolds that are Teichmueller spaces, only the four-punctured sphere can arise from the connected boundary of a hyperbolic manifold. If you have a once-punctured torus, you have to have at least two of them because the cusps have to pair up in pairs. Okay, so let me start, and I think I'll switch to using the board for a little while, by just explaining what Thurston's skinning map is all about. So what's the setting? It's going to be, so M is going to be a hyperbolic manifold with totally geodesic boundary. And for most of the lecture, I'm actually going to focus on the case where the boundary is a surface S, which will be, as it often is at the Ahlfors-Bers colloquium, a connected compact surface of genus at least 2. Okay, so a word about this totally geodesic boundary. What I mean here is that it's an infinite volume hyperbolic manifold. It has a flaring end that can be conformally compactified by a Riemann surface, but also where that end has a special type, it's cut off by a totally geodesic surface. Okay, so here's M. This totally geodesic surface is actually a hyperbolic structure on S. So such a manifold, and this is not the most general setting in which the skinning map can be defined, but it's the one all our examples will fit into. So such a manifold, by the work of many people, Ahlfors-Bers, Grab, Martin, Maskett, Sullivan, Thurston, has not one hyperbolic structure, not just the hyperbolic structure it's presented with, but a whole space of hyperbolic structures. And I'll focus on the geometrically finite ones, geometrically finite hyperbolic structures that are actually parametrized by the Teichmueller space of the boundary surface. And that map is, at least in one direction, is easy to explain. a Riemann surface structure on S, which I'll call X, corresponds to a hyperbolic structure on M that has that Riemann surface as its Riemann surface at infinity. So here is X is going to be the Riemann surface that appears in this conformal compactification. So in one Riemann surface at infinity of the hyperbolic structure. And I guess the reason that I write rho x here is that I'm going to think of it as a representation of the fundamental group of M into PSL2C, corresponding to the uniformization of this manifold by H3. Okay, so in this picture, there's at least one case in which we can understand this. If we think of this totally geodesic surface as a hyperbolic surface, that gives a point in the Teichmueller space. And for that one, the Riemann surface at infinity is also that point in Teichmueller space. In general, for a different Riemann surface structure, you'll still have a hyperbolic structure on the interior, but this totally geodesic surface will no longer be there. There will be some convex surface that bounds a compact part of the manifold that carries all the topology, but it will probably be quite different from the Riemann surface at infinity. So this parameterization, which uses the quasi-conformal deformation theory of Kleinian groups, is one of the major struggles in this project is to avoid having to understand this from a computational or numerical perspective. This map is a little bit like the uniformization theorem. Right? It associates to a Riemann surface structure some sort of rigid metric, geometric structure, and the map in any obvious coordinate system for the Teichmueller space and for the space of representations of the fundamental group of M is some highly transcendental map. So what is the skinning map all about? It's the fact that, well, just like up there, once you have one of these hyperbolic structures, you can take the cover of M corresponding to the fundamental group of the boundary. And I'll just point out that the fact that the boundary is totally geodesic means that its fundamental group injects into that of M. The boundary is incompressible. So you can take the cover of M corresponding to its boundary, the boundary subgroup pi1s, and you get a geometrically finite hyperbolic structure on the surface across the real line. That has now two hyperbolic structures, or two conformal structures at infinity. One of them is clear. Because this end of the manifold carries the fundamental group of S, it lifts to this cover, and so you see a copy of the Riemann surface X still out there at infinity. But this process of taking the cover reveals a new Riemann surface, which is, well, let's just give it a name. It is the image of X under the skinning map of M. OK, so I've just reproduced the slide that you've been looking at for the last 3 minutes on the board. But what this means as far as a mapping is that the covering construction induces a map from geometrically finite hyperbolic structures on M to hyperbolic structures on S cross I. The respective Ahlfors-Bers parameterizations of their hyperbolic structures give you a map from Teichmueller space to Teichmueller space of the surface and Teichmueller space of the surface with the opposite orientation. And this map takes X to a pair, X and some new surface, which we call sigma M of X. OK, this geometrically finite structures on surface cross interval, this is known as the quasi-Fuchsian space. So what this is saying is that the hyperbolic structures on M give you a family of quasi-Fuchsian groups. Quasi-Fuchsian groups can be thought of as pairs of Riemann surfaces. And so the pairs of Riemann surfaces that arise are the graph of a map. And that map is the skinning map. So that sigma M, as described here, is a map from the Teichmueller space of S to the Teichmueller space with the opposite orientation. This is actually a holomorphic map. And Thurston showed that if M is acylindrical, another something that follows from our assumption that it has totally geodesic boundary, but I'm stating this in the generality in which the skinning map exists. If M is acylindrical, then the image of the skinning map is a bounded subset of Teichmueller space. This is Thurston's bounded image theorem. OK, so when I said that the goal of the project was to be able to see the skinning map. In fact, what we're going to do is to try to make a meaningful picture of the image of the skinning map, a bounded subset of the Teichmueller space. By working with a four-punctured sphere, the Teichmueller space is just the upper half plane. And so we're talking about a bounded open set in the upper half plane in the complex plane. Couldn't get much more concrete than that. So let me explain the main idea in this construction. It's to interpret the statement that the skinning map maps a Riemann surface X to another Riemann surface Y as a statement about the intersection of two submanifolds in the character variety. So how is that going to work? Let me point out something that we all know from teaching calculus, that to say that some point is in the range of a function is just to say that the horizontal line with that y coordinate intersects the graph of the map. So similarly, to say that a Riemann surface y is in the image of the skinning map is really about the intersection between two sets. One of them will be the graph of the skinning map, and the other one is going to be the set of all quasi-Fuchsian groups that have that Riemann surface y as their lower conformal boundary structure. So let me try to develop that picture in a little bit more detail. So what do we have here? There's a restriction map that, well, in fact, it's defined on character varieties. So let me introduce the character variety. The character variety of S is homomorphisms from the fundamental group of S to PSL2C modulo conjugacy. So these are representations up to conjugacy, and this is where hyperbolic structures on S live. And similarly for the character variety of M. And these contain those spaces of hyperbolic structures. So quasi-Fuchsian space lives inside the character variety of S, and the space of hyperbolic structures on M lives inside the character variety of M. And I'll point out that the fact that the fundamental group of S injects into that of M, or really just maps into, induces a restriction map on character varieties, a map from the character variety of M into the character variety of S. So it's called restriction because this is just the statement that when you have a map from the fundamental group of M into PSL2C, you can restrict it to a subgroup of the fundamental group of M, like pi1 of S. So this is actually a regular map between algebraic varieties. Both of these are affine algebraic varieties. So let's think about what that restriction map does. Well, let's think about it up here. So this is all a picture of what the statement, the skinning map of M takes the point X to the point Y, means in terms of this restriction map. So here at the top, we have geometrically finite hyperbolic structures on M. I've drawn that as an interval. The idea is that interval represents the Teichmueller space of the Riemann surface S. And if you take a point in that Teichmueller space and you apply think of that point X in Teichmueller space as a hyperbolic structure on M, applying this restriction map to it is exactly taking the cover of that hyperbolic manifold corresponding to the boundary subgroup. And so you get some point here in quasi-Fuchsian space, the geometrically finite hyperbolic structures on S cross I. I've drawn that as a square because I guess in this model, Teichmueller space is an interval. And so quasi-Fuchsian space is the product of two of those, the product of two intervals. So here, this point in quasi-Fuchsian space is on the image of hyperbolic structures on M under the restriction map, this blue curve here. But it's also, if the skinning image of X is equal to Y, it's also on the bare slice of Y, this orange curve here. So I'm following Sarah's convention that if your talk is about two sets that intersect, one of them should be blue and one of them should be orange. What is the bare slice of Y? This is the set of all quasi-Fuchsian groups. So I should introduce the notation. I said that hyperbolic structures on S cross I are parametrized by Teichmueller space cross the opposite Teichmueller space, and I'll use Q to denote that parameterization. So Q of xy is the quasi-Fuchsian group that has x on one side and y on the other. So the bare slice of y, here y is a point in the Teichmueller space with the opposite orientation, is the set of all quasi-Fuchsian groups of the form q of something and y for fixed y. Okay, so that's the horizontal line in this graph picture. That's the set of all quasi-Fuchsian groups that have some surface on the bottom. And the statement that sigma m of x is equal to y is the statement that those two sets, the bare slice of y and the image of hyperbolic structures on M under the restriction map, that those two sets intersect at that point. Okay, ultimately we're going to create an image of the skinning map by answering the question, is y in the image or not? And the pre-image point, x, is going to play less of a role here. So in fact, let's forget about x for a minute and just think about this statement that the bare slice and the image of hyperbolic structures on M under the restriction map intersect. Well, the first point is that none of this is really computationally accessible. The space of hyperbolic structures, we're treating it on the surface across an interval. We're treating it as this product of Teichmueller spaces. But like I said, that Ahlfors-Bers parameterization uses the quasi-conformal deformation theory, is a kind of transcendental object. Instead, we work with these sets, the bare slice and the restriction image, in a nice algebraic variety that contains them, namely the character variety of the surface. So let's place this picture into that variety where it lives. The character variety of a finitely generated group is an affine algebraic set. It has nice explicit coordinate functions, and so it's easier to work there. But this introduces the following complication. So inside of the character variety of a surface group, you have the space of quasi-Fuchsian groups, which is an open set, but it has a very complicated boundary. And inside of that open set of quasi-Fuchsian groups, both the bare slice and the restriction image, so both of these curves that we've been considering, they're actually bounded. One of those is a consequence of Thurston's compactness theorem for acylindrical manifolds, an ingredient in the bounded image theorem. And the other one is a consequence of Bayer's inequality, which says that if you fix one side of a quasi-Fuchsian group, you bound the lengths of all geodesics in that manifold. So in fact, what we study in this problem is not directly the bare slice or the restriction image, but analytic completions of those two things. So let me start writing that somewhere. So we study analytic completions. So the idea here is that each of these sets that we want to understand the intersections between lives inside of some analytic subset of the character variety that is more directly accessible to computation. And it factors the problem into two steps. One of them is to study those analytic completions and their intersections, and then the other is to figure out which of those intersection points actually correspond to the original problem. So let me introduce the first one. Well, remember, the hyperbolic structures on M, those live inside of the character variety of M. So this blue interval here really sits inside of some affine algebraic set, and the restriction map is defined on that entire set. So the set of quasi-Fuchsian groups arising from hyperbolic structures on M, that sits inside of some algebraic subset of the character variety. So let's do that. So here we have the entire character variety of M mapping by the restriction map into the character variety of its boundary surface. Its image is some algebraic subvariety, which is this thin blue curve here. And it has, inside of that subvariety, there's an open set that's accounted for by hyperbolic structures on M. And what about the bare slice? So the analytic completion here of the image of hyperbolic structures on M under the restriction map. This is contained in what I call EM up there, which is defined to be the entire image of the character variety of M, and then you take its Zariski closure. The difference between the actual image and the Zariski closure will play no role in anything that I say. I just want to be honest here. And this E stands for extension. So we call this the extension variety because it reflects a property that a representation of a surface group may or may not have. If you have a representation of the surface group, it might be possible to extend that to a representation of this three-manifold group that's compatible with the inclusion of S as the boundary of M. Right? So you have a representation defined here. Can you extend it to the full fundamental group of M? If you can, then you're in the extension variety. And it's possible you might be in the extension variety even if you're not of that form, but you're a limit of things of that form. So that's EM. EM is an algebraic subvariety of the character variety of S. What about the bare slice? So that is contained in the holonomy variety. I have to say something about projective structures. So the bare slice of Y is contained in HY, which is the set of holonomy representations of complex projective structures on Y. What is a complex projective structure on Y? Well, let me tell you one way that you can get one. If you have a domain in the plane or in CP1, and if that domain is acted on by a group of Mobius transformations, freely and properly discontinuously, then the quotient has a natural complex projective structure. You could take that almost as a definition. And one way you could get that is you look at a quasi-Fuchsian group that has Y as one of its boundary surfaces. Then the domains of discontinuity of that quasi-Fuchsian group cover two Riemann surfaces. Y is one of them. So any point in the bare slice gives you a complex projective structure just from taking the quotient of its domain of discontinuity. On the other hand, there are many projective structures on Y that don't arise from that construction. And the full set of holonomy representations is actually a holomorphically embedded copy of a complex vector space. So this is the image of the quadratic differentials on Y under the holonomy map. And so this is where Hall from the vector space of quadratic differentials on Y into the character variety of S. This is a proper holomorphic embedding. So remembering that we're eventually going to be discussing a one-dimensional Teichmueller space, you would probably do well to think of the bare slice as a disk. Right? It's isomorphic to the Teichmueller space, and so you could think of it as the unit disk or the upper half plane. This holonomy variety in that same situation would be a complex line. The vector space of integrable quadratic differentials on a four-punctured sphere is one-dimensional. And so this is like the disk being contained in the complex plane, and all of that embedding into the character variety. Now I've drawn in this picture, I've drawn the image of that holonomy variety as some deliberately very oscillatory, complicated subset. And it's true, I mean, various things that you might think from this picture are true, that there are lots of spurious intersections between the extension variety and the holonomy variety, that this holonomy variety returns to quasi-Fuchsian space many times, that some of those returns are completely unrelated to the skinning map. But nevertheless, we now have these two analytic sets, the holonomy variety and the extension variety, and the skinning map, or rather the statement that Y lies in the image of the skinning map, is accounted for by some intersection point between these sets. Okay, so like I said, the holonomy variety is the image of the vector space of quadratic differentials. Some of that image corresponds to the bare slice. That's actually the Beer's embedding of Teichmueller space, depicted as this vertical interval here. And the space of quadratic differentials on Y is actually a fiber of the space of all projective structures. So remember, HY is just the holonomy of projective structures on the Riemann surface Y. If you allow the Riemann surface to vary, you get the space of all projective structures. That also maps to the character variety. That holonomy map is a local homeomorphism. And projective structures form a bundle over the Teichmueller space, of which this is just a fiber. So this is what I would call the kind of geometric picture, that you can understand a point that's in the image of the character variety, a point that's in the image of the skinning map, as an intersection between two analytic sets, One of them is it corresponds to this algebraic map between character varieties, the restriction map. The other one corresponds to this holomorphic map from projective structures to their holonomy representations. And the projective structures form a bundle over Teichmueller space, and you're interested in one of those fibers and whether its image intersects the extension variety. Okay, so I want to turn this now into a diagram of spaces. So at the top, we have the character variety of M. So let's get rid of the picture. At left, we have the space of projective structures. So this is a diagram of the maps we were considering. So let me introduce the other key player here. In studying the skinning map, we're interested in cases in which the holonomy of a projective structure is equal to the restriction of a hyperbolic structure on M. So that's effectively studying what you could call the inverse limit of this diagram, the fiber product of these two maps. So let me write that definition. Okay, just continue here. So what is this thing FM? This is the fiber product of those two maps. The holonomy map from projective structures on S bar to the character variety of S, and the restriction map from the character variety of M to the character variety of S. What that means is it's the subset of projective structures times character variety of M consisting of pairs that map to the same thing. So it's the set of pairs of a projective structure Z and a representation rho such that the holonomy of Z is equal to the restriction of rho. Let me just talk about dimensions for a moment. So the Bers slice, and let's say that n is the dimension of the Teichmueller space. With either orientation. Then the Bers slice is essentially a copy of Teichmueller space. So its dimension is also n. It sits as an open subset of this holonomy variety, so that also has dimension n. The space of geometrically finite structures on M is parametrized by that Teichmueller space, so that also has dimension n. And at least if we define the extension variety using the right irreducible component of the character variety of M, that's going to be the dimension of this algebraic subvariety. So what we have here are a pair of n-dimensional subsets of the character variety of S, which has dimension 2n. So asking for intersection points between these things could be a well-posed problem. You have two half-dimensional submanifolds of the character variety. You expect their intersections to be zero-dimensional. Similarly, if you think about the fact that the holonomy map is a local homeomorphism, it follows that this fiber product, F, is also n-dimensional. And it comes equipped with a projection down to the Teichmueller space. So our method is to treat that projection as something like a branch cover. So let me introduce some subsets of this. So we have the fiber product FM. Inside of that, you have the subset consisting of quasi-Fuchsian groups. Okay, so those are pairs of rho, pairs Z rho, where the holonomy of Z which is the restriction of rho, is quasi-Fuchsian. Inside of that, you have what we're really interested in, the part of the fiber product that actually comes from the skinning map. I'll call that F sigma. So those will be the set of points in this fiber product that we can construct from the skinning map. And how do we do that? So associated to a point, associated to the statement that sigma m of x is equal to y, this determines a point in the fiber product. Namely, well, we need a projective structure. So that's going to be, okay, I'll write something and then explain why it defines a projective structure. So it's going to be the projective structure on y that's induced by the quasi-Fuchsian group QXY, and the hyperbolic structure on M coming from the Riemann surface X. So it's the set of those such that sigma m of x is equal to y. All right, this is all to say that Fm is defined by a fairly nice intersection property. Two half-dimensional submanifolds of the character variety. Finding their intersections is equivalent to finding Fm. Down here at the bottom, we have a set that understanding it would be good enough to understand the skinning image completely, because it's the set of pairs of a projective structure on y and a hyperbolic structure on M, where sigma m of x is equal to y. This projects to Teichmueller space. And that projection takes the point qxy and rho x to y. So the question becomes, for which points in Teichmueller space is there a point in this fiber product that lies over them? Fiber product for sigma. So here's the one proposition that makes it all work. I call it a proposition rather than a theorem or something because it's just a translation of what the Ahlfors-Bers parameterization of hyperbolic structures on M says. So first, Fm, it's really only an analytic set, but it's a manifold in the neighborhood of the points that we care about. Fm is a complex manifold of dimension n in a neighborhood of the closure of the part we care about. 2, Fm sigma is the connected component of the quasi-Fuchsian part containing the totally geodesic boundary structure. So I said at the beginning that the manifold is given to us with a totally geodesic boundary hyperbolic structure. That means there's at least one point in this fiber product we already know. It's the one where this quasi-Fuchsian group is that Fuchsian group where rho is just the totally geodesic structure, and that lies in Fm sigma. So inside of this full fiber product, which has the dimension of Teichmueller space, you look at the quasi-Fuchsian set. That's some open set, probably a countable union of connected components. And the one that contains the base point we know gives us the graph of the skinning map. Okay, and I guess the third point is the one that makes the numerical part work out. 3. At any point in Fm sigma that lies over y in Teichmueller space that is a regular value of the skinning map, the two submanifolds whose intersections define Fm intersect transversely. Em and Hy intersect transversely. At, okay, so I should give this point a name. P intersect transversely in P. So here's how this becomes an algorithm for computing the image of the skinning map. There are two steps. The first is, let's start in the Teichmueller space of the surface and start at a point where we know, I guess I'll point to this figure. So let's start at a point in the Teichmueller space where we know some point on this fiber product, which is to say, we know that it's in the image of the skinning map already. And then we start moving outward from that point in Teichmueller space and use Newton's method to find intersections between the extension variety and the holonomy variety. Remembering that as long as we don't run into a critical value of the skinning map, that's a transverse intersection of two manifolds. It's an isolated transverse intersection of two manifolds. So what I would say is that having this base point is like having an intersection point between two manifolds. Moving in the Teichmueller space of Y is to say we deform one of those manifolds slightly. We want to locate a new intersection point. So that's a well-posed numerical problem. Finding the new intersection point is lifting a path in the base Teichmueller space to a path in this fiber product. So practically speaking, what we do is we explore the one skeleton of a triangulation of the upper half plane. We don't do anything fancy like use a triangle tiling of the hyperbolic plane because the combinatorics are slightly complicated. We do something very simple, which is we look at the equilateral triangle tiling of the plane for some fixed small size of the triangle. So marching outward from the base point, we try to lift triangles one by one to triangles in this fiber product Fm, all the while paying attention to whether we've left the connected component that consists of quasi-Fuchsian groups and which contains the base point. As soon as we've left that quasi-Fuchsian component, we're no longer in Fm sigma, and so we're no longer over the image of the skinning map in the Teichmueller space of S. So what's the output of that procedure? That will produce a simplicial 2 complex inside of the product of the character variety of M and the space of projective structures on S that approximates Fm, at least some part of Fm, and that piece is big enough to contain the entire Fm sigma, the part corresponding to the skinning map. Exactly. So here are the key steps that allow this to be done numerically. So there are really 3. The first is that Hall is computable. So what is Hall? This is the map that takes a quadratic differential and gives you the holonomy of the corresponding projective structure. So this means that Hy is also computable. And this just uses the integration of ordinary differential equations in the complex domain. Computing holonomy representations of projective structures using this method goes back to a paper of Keen, Rausch, and Vasquez, with later developments by Porter and by Yamashita and collaborators. So our implementation uses a new implementation of this ordinary differential equation solver to compute the holonomy representation of projective structures. The second point is that the map, the restriction map, from the character variety of M to the character variety of S, is also computable. And this uses at least when the fundamental group of M has at most 3 generators. This uses the so-called Fricka trace calculus. that compatible presentations for the fundamental group of M and for the fundamental group of S allow you to compute explicitly in trace coordinates what this map looks like. And finally, the following is only a slight lie, that the question of whether or not a point is in quasi-Fuchsian space is computable. Almost. So let me say what almost means. So here I'm referring only to S being the punctured torus or the four-punctured sphere. The associated representations are commensurable, so you can reduce either one to the other. And this uses a criterion of Brian Bowditch in the character variety. So here's what Bowditch's work gives. It doesn't exactly give you a way to test whether a representation lies in quasi-Fuchsian space. But it gives you a way to test whether or not a representation lies in some set B. The way the test works is that you have to recursively explore the tree of generating triples for this free group on two generators, apply some numerical test to the traces of each such triple. You eventually get some subtree, and if that tree is finite, then you're in this Bowditch set. So that gives some way of testing elements in this set. And what we know about this set is that it is an open set in the character variety, and quasi-Fuchsian space is a connected component. Conjecturally, so Bowditch conjectures that they actually agree, that these two sets are the same. And that would mean that this gives an actual test for whether a representation is quasi-Fuchsian or not. But all that we actually need in this approach is a way to test for a component of something, that the component of the quasi-Fuchsian set that contains a given point. And so for that kind of problem, just being able to test whether you lie in one connected component is enough. So all we use here is that the Bowditch set is some open set in the character variety of which quasi-Fuchsian space is one connected component. Okay. All right, so I want to demonstrate what our program does in a moment, but let me just finish up this sketch of how it works. So what is the output of this first step? It's a simplicial 2 complex that approximates this fiber product FM, and that, at least at the level of all the representations that are tested, seems to contain the quasi-Fuchsian part of it. So then we have this 2 complex. What we have to do then is test a bunch of points in that 2 complex for whether or not they are quasi-Fuchsian, say a fine mesh of points. As I've depicted in this picture, we probably get something like a few hundred triangles. But to make an accurate picture of the image of the skinning map, we then want to test, say, millions of points in a very fine mesh on this surface. Test whether each one is quasi-Fuchsian or not. And the ones that are quasi-Fuchsian, we project down to the Teichmueller space. And that produces a picture of a subset of Teichmueller space, which is the image of the skinning map. So those 2 steps are implemented in 2 different programs. First one we call the flayer for the fiber product layers. So it constructs a surface that lives in a bunch of layers like a branch cover over Teichmueller space. And the second one uses the output of that, runs that quasi-Fuchsian test on a fine mesh, and rasterizes it. It produces a bitmap image. So what I'm going to do now is demonstrate this first program. I should say, just in a word, what the example manifolds are going to be. I've said nothing about the four-punctured sphere so far. I've only talked about the generality of a manifold that has a connected compact surfaces boundary. So we work with manifolds that have a four-punctured sphere boundary. And all of the examples I'm going to show you, I think, are obtained by gluing faces of the regular ideal octahedron. So there are 4 manifolds that you can produce that have geodesic boundary by gluing 2 pairs of faces of the regular ideal octahedron, which I've shown here. So imagine of the 8 faces of the octahedron, I've colored 4 of them red. So divide those into 2 pairs, like the top pair and the bottom pair. Glue those pairs. You have a bunch of choices for how to do that, but you only get 4 different manifolds up to isometry. Of those, 3 have 4-punctured sphere totally geodesic boundary. And so those 3 examples are the ones that we focused on initially. I guess I've drawn a picture here of one of them. This is where you glue the top faces just by sort of swinging one over the top. And that, so that gives 1 vertex in the quotient. And then you glue the bottom pairs of faces with a twist. The resulting manifold is actually a genus 2 handle body. Its boundary is a 4-punctured sphere, which you can think of as the complement of two curves inside of this genus 2 surface. So this is a paired manifold, and the pairing annuli are this light blue one and the dark blue one. Okay, so in fact, all of the manifolds that you get by gluing two pairs of faces of the octahedron have this structure. It's a pair of curves in a genus 2 surface. You remove those, think of those as parabolics, and then you get a hyperbolic structure on the genus 2 handle body with totally geodesic boundary. Okay, so now I'll just demonstrate what this fiber product reconstruction looks like. Okay, so what I'm going to show you is a picture, that lives in, properly speaking, it lives in a product of the Teichmueller space and the character variety of the 3-manifold group. But I can't show you a picture of that, so I'm going to show you a picture that lives in Teichmueller space across the real line. So the Teichmueller space is just going to be this upper half plane, which is in the picture here. So that's the Teichmueller space of the 4-punctured sphere. But this is in a 3-dimensional space, and the third direction, the z coordinate here, you should think of as representing the character variety of this handle body, character variety of M. What I've done is I've chosen some trace coordinate on that character variety and used its real part as a third coordinate here. So you may see in the picture, you may see intersections between things that don't represent genuine intersections in the character variety because there are other coordinates that would separate them. But it's an attempt to make a meaningful 3-dimensional picture of what's happening in this fiber product. So what happens in the program is that we start with some triangle in the Teichmueller space, one point of which corresponds to the totally geodesic boundary structure of M. So that point comes equipped with a lift into this fiber product that we already know about. And then the algorithm is going to just march outward in the triangle tiling, and one by one try to lift triangles into the fiber product, first by lifting the one skeleton, and if it observes no monodromy, filling it into an actual triangle. So I'll show you an animation of that process. So warning, the animation I'm going to show you is not in real time. The program is not running right now. What I will show you took about 10 minutes to compute, but I didn't want to have 10 minutes of it running during the lecture. So we'll start out very slow and then gradually speed up. Okay, so what's happening is it's exploring the Teichmueller space of the 4-punctured sphere, one triangle at a time, and lifting those triangles to this surface that lives inside the product of projective structures and the character variety of M. So the kind of dark blue surface that's being constructed here represents this fiber product. So what do the colors mean? Dark blue means that every representation that's been observed in that triangle is quasi-Fuchsian. Pretty soon, we're going to start seeing some white triangles appear. A white triangle means it seems that we have left Teichmueller space in that no representation that was explored in that triangle was quasi-Fuchsian. Do we have any of those? Well, actually, something interesting already happened. It appears that this projection of the fiber product to Teichmueller space has a branch point, which would correspond to a critical point of the skinning map. So you can see this local behavior of the projection would look kind of like the map z goes to z squared. Okay, so I think some white triangles are starting to appear. I'll freeze it there. So that means it's going to stop exploring once it finds that we've left the connected component of the quasi-Fuchsian set containing the base point. Light blue triangles, if you see some of those are kind of boundary triangles where some representations are quasi-Fuchsian and some are not. It's almost done now. So what's the end result? It's a finite simplicial complex, this one, equipped with an explicit projection to the Teichmueller space of the 4-punctured sphere, such that if you look at this complex and figure out which subset of it is quasi-Fuchsian, the connected component of that set containing a base point projects exactly to the image of the skinning map. All right, so this is the output of the first step in that algorithm. The second step is to then look at this surface, choose a fine mesh inside of each triangle, and then really test carefully which of those points are quasi-Fuchsian, which are not, record all of the quasi-Fuchsian ones, and then project every single one of them down to Teichmueller space. One way to think of this is that this is a coarse image of the skinning map. It has only the resolution of the number of triangles that we've developed here. But then we can do a very careful test in each triangle to get a fine, high-resolution image of the skinning map. So that's what I'll show you now. And notice that there is a hole in this surface. Let me see if I can show you. You see, hole right there. That's because there was a triangle whose one skeleton lifts to this fiber product with non-trivial monodromy. So that wasn't filled in, and that represents a critical point of the skinning map, where the derivative of the skinning map is 0. Or at least it seems to represent that. That was later proved that that's actually there in Jonah Gaster's thesis. Okay, so now I'll show you just a few skinning map images that were produced by this process. So first, the example that I showed you before, this exact hyperbolic manifold, where it's the genus 2 handle body with these two curves drilled out as pairing annuli of rank 1 cusps. This one turns out to have a rectangular boundary. I refer to a Riemann surface structure on the 4-punctured sphere as rectangular, exactly if it's the double of a rectangle across its boundary and then removing the vertices. So here, this is not the image that you were just seeing. This is another skinning image. And it's a bounded, open subset of the Teichmueller space. It lies in the upper half plane. The region you're seeing in this picture is from -2 to 2 on the real axis and 0 to 4 on the imaginary axis. So that's the complete image of that skinning map. Okay, so I just want to show a comparison between two things. This is the image of, this is the actual skinning image, where the blue points represent there is a pre-image of that point under the skinning map. But this was constructed by looking at the projection of some big 2 complex inside of the fiber product. And so a bunch of points here, the gray ones, were inside the fiber product, but when they were projected, they did not represent quasi-Fuchsian groups. So just for each picture that I show you, you should imagine that there's some surface living over it, and the blue part is the quasi-Fuchsian part. And this gray part corresponds to points that were in the fiber product, but not in the graph of the skinning map. So here's a closer view of that one. These pictures can naturally be drawn in the unit disk model of the hyperbolic plane because each one comes equipped with a base point. The manifold has a totally geodesic boundary structure. It has exactly 1. So it makes sense to draw these in the unit disk model centered at the totally geodesic point. So here's a picture for the first manifold with the rectangular boundary. So this particular hyperbolic manifold with totally geodesic boundary was studied by Cheeseborough and Deblois, their work on trace fields and commensurability of link complements. Okay, so the second one is the one I just showed you the demonstration of. And now you see that when you project it down to Teichmueller space, some points are covered twice, some points are covered once. This skinning map has a critical point where it locally wraps 2 to 1. And if you like, the boundary of Teichmueller space maps to a simple closed curve that, maps to a closed curve that looks something like this. It wraps around this point and then continues. So this is drawn in the same region in the upper half plane. There's the projection of the full fiber product surface. Here's a closer view. That hole is not really a hole in the image. It's, in fact, that hole is showing you where the critical point seems to be. And here it is in the unit disk model. Finally, this is my favorite of the minimum volume hyperbolic manifolds with totally geodesic boundary. This is the one where you glue both pairs of triangular faces with a twist, and you do it in a symmetric way so that the boundary surface ends up being the square 4-punctured sphere. Square meaning you double a square across its boundary and then remove the vertices. This one gives what to our eyes was a very strange region in the upper half plane. It looks less symmetric than any of the others. This was also the most computationally challenging one, and you can see that the algorithm had trouble constructing the fiber product when it was entering the thin parts of Teichmueller space, but it got just close enough to be able to compute the full skinning image. And we were perplexed by this picture, thinking this seems to be the most symmetric hyperbolic structure. Why did it give the least symmetric skinning image? But then, of course, we drew it in the unit disk model. And we realized, the upper half plane is a highly distorted way to view a subset of the hyperbolic plane that has a distinguished point. So in fact, it's a nice symmetric image after all. And there's the image of the full fiber product in that same model. OK, so these are the 3 hyperbolic manifolds with 4-punctured sphere boundary that arise from the regular ideal octahedron drawn in the same coordinate system, red, green, and blue. And I just wanted to show you one more example of how we might use this visualization technique to develop conjectures or try to understand the behavior of skinning maps a little bit better. So remember that the examples I showed you before all have the following simple form. It's a genus 2 handle body. A pair of curves are drawn on its boundary genus 2 surface. Those curves are declared to be rank 1 parabolics. And then you get a hyperbolic manifold, at least if the 2 curves are chosen correctly. So one thing that you could do to create a family of such manifolds is to take a fixed pair of curves and then apply mapping class group elements of the genus 2 surface to them. Actually, it only matters which element of the mapping class group up to as a coset of the handle body group, but nevertheless, I'll refer to them as applying actual elements of the mapping class group. So we considered what happens if we take that first example I showed you and apply Dane twists in one curve to the pair and to get a family of hyperbolic manifolds with totally geodesic boundary in which the pairing annuli are getting more and more complicated. So for the first few Dane twists, we could draw their skinning images. I know it looks like 3 simple pictures here, but in fact, the degrees of the algebraic maps involved are blowing up very quickly. In fact, they blow up even more quickly if you look at pseudo-Nosov maps, and that's why we didn't consider a pseudo-Nosov example. But for these first 3 examples, they all seem to look quite similar. And in fact, this led us to conjecture that if you just look at the manifold in which you drill out the geodesic representative of the curve you're Dane twisting along, that it has its own relative skinning map. This is a manifold with a rank 2 cusp. So I'll just quickly draw a picture of what manifold we're talking about. Now it's a manifold in which you take the genus 2 handle body, you drill out some curve inside the handle body, and then you draw some other curves on its boundary, which are going to be pairing annuli of rank 1 cusps. So this thing also has a skinning map, and we're able to produce an image, the image of that skinning map. And that seems to be the limit, at least for these first few examples. It seems that there's a kind of geometric convergence for these skinning maps in these Dane twist families. And so this was, this limiting picture is an ongoing joint project with Jonah Gaster and Richard Kent. And after the fact, we realized that if you just believe that every theorem that's true for Riemann surfaces that are compact is also true for Riemann surfaces with cusps, then this would follow from a result of Richard Kent. So he proved that in Dane twist families, you have uniform convergence of skinning maps, though in Dane filling families, you have uniform convergence of skinning maps, though his results applied specifically to surfaces without punctures. So, OK, so I think I'm almost out of time. I'll just say that there is work in progress here. The next thing that you might try to do is consider a manifold that has 2 different boundary surfaces and look at slices of its skinning map image. So there's a natural way to produce a hyperbolic manifold with 2 4-punctured sphere boundary surfaces by gluing faces of the regular ideal cube octahedron in hyperbolic space. And we considered slices of this where you look at the diagonal in the bidisk, which is the Teichmueller space of the boundary here, and various rotations of it. And you get a family of slices. But unfortunately, our program has some trouble lifting triangles here. So we don't yet have a full image of this skinning, even slices of this skinning map image for the cube octahedral manifold. OK, so I'll just end by saying that this was all implemented in Python with a little bit of C and Cython used to write an extension, that the CP1 structures library that was used is already open source, and you can find it on my GitHub page, and that the Flair, this fiber product layer reconstructor, will be open sourced as soon as we're done with it. OK, thank you.